You think you know what empty means. You don't. Right now, you're sitting in a room or walking down a street or lying in bed, and you believe that between you and the wall, between your hand and your face, between the atoms in your skin and the atoms in the air, there's space, empty space, nothing, a gap where nothing exists. You're wrong. Profoundly, beautifully, disturbingly wrong. And the person who would have loved telling you exactly why you're wrong, with that mischievous grin and that unstoppable clarity, was Richard Feynman. Because Feynman understood something that still makes physicists uncomfortable when they think about it too long. He understood that the emptiness you take for granted, the void you assume exists between every particle of matter in the universe, is actually seething with activity, roiling, boiling. A kind of quantum madness that never stops, never rests, and fundamentally cannot be turned off. The space between particles isn't empty. It's the most full thing in existence. Let's start with something you can touch. Hold your hand up. Look at it. You see solid flesh, don't you? But you already know that's an illusion. You've heard this before. Your hand is mostly empty space. The atoms that make up your skin, your bones, your blood, they're almost entirely nothing. The nucleus of an atom is tiny, impossibly tiny, and the electrons orbit at distances that are, relatively speaking, astronomical. If an atomic nucleus were the size of a marble sitting at the center of a football stadium, the electrons would be little more than whispers circling somewhere near the top rows. Everything between the nucleus and those electrons, you've been told that's empty, a void, nothing there. But here's where the story you've been told starts to crack. Because when physicists started actually looking at that space, not with their eyes, not with microscopes, but with the mathematics of quantum mechanics, they discovered something impossible, something that shouldn't exist if empty truly meant empty. They discovered that even when you remove everything, every particle, every atom, every photon of light, every vibration, every whisper of energy, even when you create a perfect vacuum, the coldest, darkest, most isolated box of space imaginable, it's still not empty, not even close. Quantum field theory tells you why, and it tells you in a way that sounds like madness at first. You see, particles, electrons, quarks, photons, all the little building blocks of matter and light, they aren't really particles at all, not in the way you think of them. They're excitations in fields. Think of it this way. Imagine the surface of an ocean. The ocean itself is always there, filling every corner of its domain, undulating, present. A wave isn't a separate thing from the ocean. It's the ocean doing something. It's the ocean moving, rising, expressing itself in a particular way at a particular place. Particles are like that. They're ripples, excitations. The universe is filled with fields, electron fields, quark fields, electromagnetic fields, and these fields are everywhere, not just where particles are, everywhere. The field exists in the space between your atoms. It exists in the space between galaxies. It exists in the so-called vacuum of space. And here's the thing Feynman would lean in and tell you, his eyes bright. These fields can never be completely still. Never. The Heisenberg uncertainty principle, you've heard the name, maybe you've even heard the idea. It tells you that there are pairs of properties in the quantum world that cannot both be known precisely at the same time. Position and momentum, energy and time. The more precisely you know one, the less precisely you can know the other. It's not a limitation of your measuring tools. It's not because the universe is hiding information from you. It's because the universe itself doesn't have that information. The properties themselves are fundamentally uncertain, blurred, indefinite. Now apply that to a field in empty space. If the field were perfectly still, perfectly at zero energy, perfectly calm, you would know its energy exactly, zero. But if you know the energy exactly, you've violated the uncertainty principle. You can't know both the energy and the time evolution of the field with perfect precision. So the field can't be still. It has to fluctuate. It has to jitter. Even at absolute zero, the coldest possible temperature where you might think everything would freeze into perfect stillness, the fields still shake. They have what's called zero-point energy. The lowest possible energy state isn't zero energy. It's the smallest amount of energy that the uncertainty principle will allow. And so the vacuum, the empty space you thought was nothing, is actually a roiling sea of quantum fields, all of them trembling, all of them fluctuating, all of them filled with this irreducible, unavoidable, zero-point energy. Feynman had a way of describing this. He'd talk about virtual particles. Now, the name is misleading because it makes you think of ghosts, of things that aren't quite real, but they're as real as anything in quantum mechanics gets. These virtual particles pop into existence out of the vacuum, exist for the briefest instant allowed by the uncertainty principle, and then vanish back into nothingness. A particle and its antiparticle, an electron and a positron, for example, can spontaneously appear out of empty space, borrowing energy from the vacuum itself. They exist for a time so short it's almost meaningless to talk about. And then they annihilate each other, paying back the energy they borrowed. The universe's books balance. But for that flickering instant, they were there. They were real. You're not hallucinating this. This isn't metaphor. This isn't philosophy. Physicists have measured it. The Casimir effect is one of the most beautiful experimental confirmations of this madness. Take two uncharged metal plates and place them very close together in a vacuum. You'd think nothing would happen. After all, there's nothing between them, right? No particles, no forces, nothing pushing or pulling. But the plates move together. They're attracted to each other by a measurable force. Why? Because the vacuum between the plates isn't the same as the vacuum outside the plates. The plates are so close together that only virtual particles with very short wavelengths, very high energy, can pop into existence between them. But outside the plates, in the larger expanse of space, virtual particles of all wavelengths can appear. So there's more quantum activity, more pressure outside the plates than inside. The vacuum itself pushes the plates together. Empty space exerts pressure. Let that sink in. The void has weight. The nothing pushes, and it gets stranger. These fluctuations, this quantum foam of appearing and disappearing particles, they affect everything. They affect the properties of real particles, electrons, for instance. The way they interact with electromagnetic fields is slightly different than you'd expect based on simple equations. Why? Because an electron isn't just an electron floating in empty space. It's an electron surrounded by a cloud of virtual particles that briefly pop into existence, interact with it, and disappear. The electron is constantly surrounded by a seething halo of its own making, a fuzzy edge where the distinction between the particle and the vacuum starts to blur. Physicists call these effects quantum corrections, and they've measured them to astounding precision. The agreement between theory and experiment, predictions based on these virtual particles, and the measurements made in laboratories is some of the most precise agreement in all of science. We're talking about predictions accurate to 10 decimal places. This isn't speculation. This is reality, measured and confirmed over and over again. You might be wondering, if all this energy is everywhere, in every cubic centimeter of space, why don't we notice it? Why doesn't it weigh us down, crush us, blow us apart? That's a deeper question than you might think. In fact, it's one of the most profound unsolved problems in physics. When you try to calculate how much energy should be in the vacuum based on quantum field theory, you get an answer. And that answer is preposterously large, absurdly, catastrophically large. If you actually added up all the zero-point energy of all the quantum fields in a given volume of space, the number you'd get is so huge that the entire universe would collapse into a black hole. But it doesn't. Obviously, you're still here. So what's going on? Physicists don't really know. The best they can do is say, well, we only measure changes in energy, not absolute energy. So maybe there's some reason we can just ignore that huge number and focus on the differences. But that feels like cheating, like sweeping the problem under the rug. And it might be connected to dark energy, the mysterious force that's causing the expansion of the universe to accelerate. Dark energy looks a lot like vacuum energy. Like the universe's empty space has a built-in pressure that pushes galaxies apart. But the amount of dark energy we observe is tiny compared to what quantum field theory predicts for the vacuum. Tiny by a factor of 10 to the power of 120. That's not a small discrepancy. That's a catastrophic failure of prediction. It's called the cosmological constant problem, and it's one of the deepest puzzles in physics. Feynman, if he were still here, would probably throw up his hands and say something like, "We don't know." And anyone who tells you they do is lying or confused. But here's what you do know. Here's what the mathematics and the experiments both scream at you. The emptiness you've taken for granted your entire life is a lie. It's a perceptual trick, a limitation of your senses, a failure of your intuition. You live your life assuming that when you see nothing, there is nothing. But the universe doesn't work that way. The space around you, the space between your atoms, the space between stars, the space that fills the incomprehensible vastness of the cosmos. It's not a stage on which events happen. It's not a passive container. It's an active participant. It's alive in its own strange way. It seethes, it fluctuates, it creates and destroys, borrows and repays, pushes and pulls. And you are not separate from it. You are made of the same fields. Your electrons are excitations in the electron field. The photons that allow you to see are excitations in the electromagnetic field. The quarks that make up the protons and neutrons in your body are excitations in the quark fields. You are not a thing standing in space. You are space doing something. You are the universe, localized, condensed into a particular pattern that has learned to ask questions about itself. When you move your hand through the air, you're not moving through emptiness. You're moving through an ocean of fields, and those fields are interacting with the fields that make up your hand. When light from a distant star reaches your eye, it hasn't traveled through nothing. It's been a ripple in the electromagnetic field, propagating through the vacuum that isn't a vacuum at all, disturbed and jostled by virtual particles the whole way. Feynman understood this. He understood that the universe is far stranger than common sense allows. He understood that the questions we ask, questions like, what is the space between particles made of, often reveal that our language, our concepts, our very way of thinking about the world is inadequate. The universe doesn't owe you an explanation that makes sense in terms you're comfortable with. It just is what it is. And what it is, in this case, is deeply, beautifully weird. There's a particular kind of humility that comes from really understanding this, not just knowing it intellectually, but feeling it. You realize that your intuitions about the world, built over millions of years of evolution, honed to help you survive in a world of medium-sized objects moving at medium speeds, those intuitions are not guides to ultimate truth. They're tools, useful tools, but limited. When you peer into the very small or the very large or the very fast, those tools break. And you're left with mathematics, with experiments, with careful reasoning that leads you to conclusions that sound like madness. But the madness is true, the emptiness is full, the vacuum churns, and you, standing in it, breathing it, made of it, are part of the strangest, most improbable, most wondrous thing in existence. A universe that is never, ever, for even a single instant, truly empty. Think about that the next time you look up at the night sky. The darkness between the stars. It's not empty. It's singing with energy you can't see, dancing with particles you can't detect, filled with a kind of presence that has no name in any human language. The void is not void. It never was. You are not surrounded by nothing. You are immersed in everything, and the boundary between you and the rest of the universe is far more fragile, far more permeable, far less meaningful than you ever imagined. That's what Feynman would tell you. That's what the mathematics tells you. That's what the experiments confirm. The empty space between particles is not empty. It's where the universe becomes most honest about what it really is. A field of infinite potential, endlessly creating, endlessly destroying, endlessly present. And you've been standing in it all along.